So good morning and welcome back to Classical Mechanics 1 at CMI. This is our 9th lecture on Tuesday, the 30th of August, 2022. Yeah, so I'm very glad that you put in the effort to work through the first 3 problem sets. The last one is being graded. We are planning to have a sort of a tutorial session to discuss the problems from the third one. This is planned for tomorrow at 10 a.m. Details will be shared with you. The idea is that each problem will be discussed briefly, and you can share any questions you have. Rather than do it in the class now, because then I will not have time to discuss the remaining material. Okay, any questions before we continue? Okay. Yeah, as mentioned before, attendance is required. It contributes to your grade, and besides your grade, it contributes to your understanding. And yeah, it's an efficient way of learning the material as well. But I make no secret of the fact that it will contribute to your grade. And I do keep track of who is present, and really appreciate your questions and participation. Okay, so I'll just share my screen. Yeah. So last time we were discussing a few things about the calculus of vectors. We introduced the concept of a scalar field, which is just another name for a function, a real valued function in this case, defined in all of three-dimensional Euclidean space. And then we had the idea of a vector field, which is basically an arrow with a certain length at every point of your space. It could be a plane as well, or three-dimensional space. And this pattern of arrows together defines a vector field. And as somebody asked, the word field is used here to denote a quantity that depends on location. It has nothing to do with the algebraic concept of a field, like you meet with the field of rational numbers or real numbers and so on. Okay, then we defined the gradient of a scalar field, which is a way of constructing a vector field given a scalar function. So this was denoted nabla phi or grad phi, and it was in Cartesian variables. It was just a vector whose components are the partial derivatives. So there we are. We worked out a couple of examples of gradients, and I will give you more in the upcoming homework. And then we introduced a very interesting geometric interpretation of the gradient, which was motivated by the examples. And the summary of that was that at any location R, the gradient is a vector that points in the direction of most rapid increase of the function phi. Okay. So this is the interpretation. We did establish it through a brief argument using infinitesimal analysis. Irrespective of whether you followed that argument, the slogan itself is very valuable, and I encourage you to understand its statement and keep it in mind. And of course, please do go through the argument and reconstruct it for yourselves. And as somebody pointed out, the function phi is sometimes called a potential function. We will explain why that is the case. And in that case, the surfaces on which phi is constant are called equipotential surfaces. Yeah. So if phi is a function of 3 variables and you impose the condition phi equal to 2 or phi equal to 7.5, that will select out a surface, a 2-dimensional surface in 3-dimensional space, and that surface is called an equipotential surface on which the potential takes equal values. Okay, now I want to discuss another construction that will now go beyond. Now that we do have the idea of differentiation of vectors, at least one kind of differentiation, we can also now talk about, I would like to say something about integration as well, briefly. So here I want to introduce what is called a contour integral, or a more colloquially a line integral. So given a vector field V, and let's work in Cartesian variables, it has some components at every point in 3-dimensional space. So given a vector field on the one hand, and on the other hand, we are also given a parametrized curve, gamma of t. So gamma of t at every point is specified for you. Of course, we have some origin in the background, that is fine. So gamma, of course, is a curve. So at every time t, it is located somewhere, and we will call that place x, y, z. Those are the Cartesian coordinates of the point on the curve. And let us parameterize t. Let us parameterize the curve by t, and suppose the parameter is chosen to run from 0 to 1. That is just for convenience. Now, using these two objects, namely the vector field itself and the curve, it is possible to define the contour integral of V along gamma. Okay, so this is the output finally is a real number. Let us say which real number it is. So we take the vector field and then we take gamma. Now from gamma, I can construct a vector. Okay. In fact, let me, so first of all, the symbol is V dot d gamma. All right, so this is the symbol V dot d gamma integrated over gamma. Right, so that is called the contour integral or line integral. Now, what is the definition? Let me write it in the next equality. So we take the vector field V and dot it with a certain vector. All right, and the result of that dot product will be a number. Of course, it's a number that depends on t. So at each point along the curve, you get a number. And then I integrate that along the curve. That is, I integrate dt to get some final output number. Now, I might need to say what this d gamma dt is. Well, geometrically, d gamma dt is the tangent vector to the curve. So let us see that. So this picture should help us a bit. So this is my curve. I have shown it to you here. Along the curve, of course, the first point on the curve is simply gamma of 0. The last point, the end point, is gamma of 1.
Okay.
Yes, please.
What you were saying, I mean, due to network issues, I could join this.
Okay. Sorry, I didn't catch your name. Who was speaking?
Onkon
Mukherjee. Yeah. So let me repeat. We are defining the concept of a line integral. This is a gadget. I mean, this is an integral, as the name suggests, along a contour. And it's a number. At the end of the day, it's a number. It's a number obtained by combining a vector field, which is specified for you, namely V of r, and a curve gamma. Now, this is the curve gamma in our example. Along the curve, you will notice that you have got the tangent vector at every point. Okay, so that's basically the velocity vector of the curve. If you think of this curve as the trajectory of a particle, so gamma of t is the position of the particle, position vector of the particle, then d gamma dt, dt is the velocity vector of the curve, or the tangent vector to the curve at point gamma of t. Okay, so gamma is the position vector of the point along the curve. At that point, you've got a tangent vector. You got another vector at the same point, namely the vector v. The velocity vector, sorry, the vector field v is also specified to you. It points in some direction. So you've got two vectors at any point along the curve, namely the tangent vector to the curve and the vector field vector. So there is a natural combination you can take, namely the dot product of the two. Suppose I take the dot product, it will give you a number at that location and simply integrate that number along the curve. Okay, so I've written it out now in components, more detail. So V is of course some Vx, Vy, Vz, and I dot that with d gamma dt, which should be the triple x dot comma y dot comma z dot, or where each of these is differentiation with respect to time. So the dot product will give you Vx dx dt plus Vy dy dt plus Vz dz dt. So add those three, it gives you some number which depends on time, and integrate over t. Okay, so I hope the definition is clear. So it's really a simple and very natural idea, combining the idea of a vector field, the tangent vector to a curve, and the dot product. Okay. So as I said, gamma dot or d gamma dt.
What does this represent?
Was there a comment?
Yeah, what does this integral, what does it represent?
I will tell you what it represents. If we think of the vector field V as the force field, like the gravitational force field in this region, and gamma as the position vector of a particle that's moving in that force field, then this integral represents the work done by the gravitational force field in moving the particle from the initial point to the final point. Okay, so that is a very valuable interpretation of this integral. But the integral can enter in other ways as well, not necessarily as the work. But this is a good model to keep in mind. Okay. Any other question? I should emphasize a couple of distinctions. One is that the vector field V is defined everywhere. Okay, so the vector field V is defined everywhere in the space. But d gamma dt, this tangent vector to the curve, is defined only along the curve. Okay, so that is not defined on points off the curve. But we don't need it at points off the curve. We only need it along the curve. Okay, now for instance, suppose gamma is a helical path, helical curve. That is one that looks like a spiral staircase. Yeah, and we can write a explicit coordinate expression for it, cosine t sine t comma t. So cosine t sine t will go round and round in a circle, and t will increase the z coordinate uniformly in time. Yeah, so in effect you will get a spring or a helix. Okay, so suppose we take that example, then d gamma, the symbol d gamma has a meaning. You should think of it as what I call the differential. I introduced the concept of a differential. So in practice, it is very simple to compute. You simply take this expression and differentiate everything with respect to time. You will get a new triple minus sine t, cosine t, and 1 times dt, of course. All right. So when I differentiate a function of time, I will get the derivative times dt. This was how we introduced the concept of a differential. So we may regard d gamma as a differential of the map gamma taking the interval 0, 1 to R3. Okay, so for those who are comfortable with this kind of thought process, it is here for you. Okay, any question about my definition of the line integral? Okay, as I mentioned, the work done by a force field F in moving a particle along a curve gamma is, of course, an important example of a line integral. So the work done WF of gamma is integral F dot d gamma. So That is in many ways the most
So it
important.
also appears in Maxwell's equation.
Oh, definitely, it appears in yeah, you're right. Yeah, it is used in defining concepts in magnetism as well as yeah, in electricity and magnetism. Yes.
Yeah, the definition is also used for quantum integrals and complex analysis.
Oh, definitely. You're quite right. Yes. If we confine ourselves to a two-dimensional plane, and yeah, we can similarly define a similar concept over there. Yeah. So that is why I use the term contour to remind you of such things. Yeah. So yeah, the F need not be the gravitational force field. It could be some magnetic field. Yeah. So then you would be computing some property of the magnetic field associated to this curve. Yeah, so it does enter very much in magnetism. As well as in electricity. So E could be, electric field could be the F. Okay. Yeah, now in general, okay, so we've now defined it, and you have given me some nice examples. In general, the line integral depends on the values of V all along the curve. I mean, after all, the definition involved in integral all along the curve, so presumably you need to know V all along the curve. However, something remarkable happens if V is a gradient vector field, that is the gradient of a scalar. Yeah, suppose we are looking at such a vector field, which is the gradient of some phi. Yeah, so phi may be some kind of potential function from which you're obtaining a force. Yeah, we will talk more about that briefly. I mean, in the upcoming discussion. But let us suppose that V is the gradient of some scalar. Then the line integral can be evaluated in terms of the values of the potential function phi at the endpoints. So something very remarkable happens when the vector field is a gradient of a scalar. In that case, the answer, it turns out, by answer I mean the line integral, does not depend on the whole curve. It only depends on the values of the potential function at the two endpoints. Now let us argue why that is the case. Let's go back and write the line integral. It was integral over gamma v dot d gamma. So for v, I substitute gradient of phi. All right, and now let me go back and write the explicit formula for this dot product. So I'm taking the dot product of the gradient, and the gradient, you recall, had three components. It was d phi dx, partial phi partial y, and partial phi partial z. Okay, so those are the three components. And we also have d gamma having three components, which is x dot, y dot, and z dot. Okay, so then when we take the dot product, we will get three terms here: partial phi partial x times dx dt, partial phi partial y dy dt, and partial phi partial z dz dt. Okay, and then of course integrated over time. All right, so this is our line integral in the special case where the vector field is the gradient of a scalar. Now something miraculous happens. These three terms, in fact, can be combined using a certain rule or identity from calculus. Do you want to tell me what that rule is? Which you may be familiar with from one variable calculus. We are now using it in three variable calculus.
Same rule.
Yeah, this is the chain rule. So who answered that?
But here is
Vishnu Ravi, sir.
Wait, one at a time, please. So who offered the name chain rule?
Vishnu Ravi, sir.
Vishnu Ravi. Thank you very much. Yeah, yeah. Mukherjee, you had a question? Yeah.
At first it looked like symbol, but here there is del x in the denominator and dx in the numerator.
Numerator. Yeah. So no, are you? No, I don't understand. What are you suggesting?
No, I mean, it looks like chain rule, but it is not actually chain rule.
Okay, I would call it the multivariable calculus chain rule, if you would like to have a precise name for it. Let me just remind you what the chain rule is. If you have a function phi, which is a function of another function of time, all right, phi of x of t, and your objective is to compute d phi dt, then the chain rule says that you can first differentiate phi with respect to its argument, and then differentiate the argument with respect to time. Okay, so this is the chain rule in one variable calculus. Now we extend this to 3 variable calculus, and I presume this will be a topic that will be dealt with more carefully in your calculus or analysis courses. So if phi is a function of 2 variables, namely x of t and y of t, both of which depend on time, and our objective is to compute its derivative with respect to the time variable, then you have to look at how phi changes due to a change in x as well as due to a change in y. You have to account for both. And to make a long story short, the answer is that this is a sum of 2 terms, partial phi partial x times dx dt plus partial phi partial y dy dt. Okay, so my objective is not to prove this formula, but just motivate it from your knowledge of one variable calculus. And the notation is very well chosen, as Mukherjee has just pointed out. The dx in the numerator and the dx in the denominator are so placed that you should think of them as cancelling each other out and finally giving you d phi dt. Okay, so I mean, that is a very a way to remember the formula if you wish. Of course, it is a sum of terms because phi depends on time through x as well as through y. So one has to account for both contributions. And if there's a third variable in phi, you have to add the third term as well. Okay, so I hope the statement of the chain rule is understandable. Yeah, so I now intend to use the chain rule. Yeah, over here, to recognize that if phi is regarded as a function of the location of the particle or the position along the curve, then this sum of 3 terms is simply d phi dt. Okay, so that is what it is. Yeah, we can always think of phi as a function of time rather than as a function of position. We have both viewpoints. Okay, so now we use the a so-called fundamental theorem of calculus, which tells you how to integrate a derivative. Yeah, and it tells you it is simply the integrand or the the function evaluated at the upper and lower limits of integration. Okay, so this is the familiar. This is called the fundamental theorem of calculus, but I am sure you have seen it in some in some guise. Integral of a derivative is the values of the function evaluated, the endpoints subtracted. So here we are. It's phi of r of 1 minus phi of r of 0. Okay, so that is what 0 and 1 mean. I have to evaluate it at the initial and final locations. So what have we achieved? We have achieved something remarkable, an expression for a line integral in terms of the values of the potential function at the endpoints, nothing more. You don't need to know anything about the curve. In fact, you can even modify the curve. You may have had an initial curve like this. You calculate its line integral for a given vector field, which is a gradient of a scalar. Yeah, and then you modify that curve, holding the endpoints fixed. The answer, the value of the contour integral will not change. Oh, all right. Any question about this?
I think this is why work done does not change. I mean, does not depend on the path.
Correct.
between two
The
points.
provided, of course, that the force be of a very special sort, namely the force is the gradient.
Conservative.
Indeed. So such a force is called conservative. So let me mention that. Yeah. So yeah. By the way, before I mention that, let me just say one more very quick remark. That is, suppose you consider a closed curve. Yeah. In particular, if gamma is a closed curve, namely r of 0 and r of 1 are the same, then the line integral of a gradient vanishes because, I mean, first of all, this is denoted by this little circle around the integral sign, yeah, to denote a integral over a closed contour gamma. All right, so such a thing is denoted in this manner. And by definition, this is phi of gamma of 1 minus phi of gamma of 0, but gamma of 1 and gamma of 0 are the same, and therefore this is 0. Okay, so so the line integral of a gradient along a closed curve vanishes. Yeah.
So one thing, where does phi come? One thing is, where does phi come in? I mean, we had vector field and a parameterized curve gamma t.
Yeah. Okay. We had a vector field, but then we specialized to a very distinguished class of vector fields, namely those that are gradients of scalars. Right. The result I am discussing now only applies in that case. More general vector fields do not possess this property. All right, great. Now let me introduce this. Just say what Oncon and others were pointing out. A vector field that is the gradient of a scalar field is called a gradient vector field. Okay, so that is the name. Now in mechanics, if a force field f of r is the gradient of a scalar function, yeah, which is usually called a potential phi of r, then such a force field is called conservative. Okay, so that is the definition of a conservative force field for us at present. And as a consequence of the result I just now discussed, the work done by a conservative force field in moving a particle along a curve depends only on the initial and final locations of the particle and not on the details of the rest of the path taken. Okay. In particular, the work done, a conservative force field does no work in moving a particle around a closed curve. Right? So, so gravity is an example of a conservative force field. Gravitational force is the gradient of a scalar function. That phasor function is basically mass times acceleration due to gravity times the height. For those who have seen this before, yeah, to some approximation that is decent. So the gravity will not do any work in the moving a particle through a closed curve if that happens. All right, but there are not all force fields are conservative. For instance, frictional force is not a gradient of a scalar. Yeah, so frictional force, friction does work moving a particle, but the gravitational force field of the Earth-Sun system does not do work when the Earth goes around one orbit around the Sun. Okay, so that is an example. I mean, if there was work being done, then there will be a loss of energy, and you might suspect that the orbit of the Earth could not be maintained in that manner. Yeah, so okay, so much for this concept. Any questions about it?
Sir, when we will deal with such problems, will we assume the force to, like, will we work out whether the force is a gradient of some potential, or will we assume that it is a gradient of some potential?
See, it depends on the context. See, somebody may tell you here is a force which is a gradient of a potential, and then you can easily use this theorem to discuss it, the work that it can do. Yeah, but you may be in a different situation where you are only provided the force, or you are experimentally determining the force by asking how do particles accelerate. And then it's not clear a priori whether that force field is conservative or not. You would have to compute the work done in many cases and then conclude whether the force field is conservative or not. So it really depends on the setup and what kind of problem you are addressing.
Thank you, sir.
Yeah. Was that Ryan?
Yes, sir.
Okay, fine. All right. Any other question concerning this? Okay, so with that, I conclude our discussion of some kinematical and mathematical preliminaries.
Can you move? Can you go up a little?
Yes. Is this okay?
No, more.
Okay.
Yes, sir.
Yeah. Okay. So do you have a question or?
No, it's okay.
Okay, so you have seen what you want to see. Anyway, so in the last 8 lectures, we have discussed various concepts concerning vectors and some of their properties, dot and cross products. We've talked about Cartesian and polar coordinates, both on the plane and three-dimensional space, as well as concepts of position vectors, acceleration, velocities, and so on. And finally, a little bit of vector calculus as well. Okay, now I come back or come to discuss some of the foundational aspects of mechanics in the context of Newton's laws and forces. All right, so let me mention a few important background concepts that underlie Newtonian mechanics. Many of these things, hopefully, you are familiar with from your day-to-day experience and previous studies. So I'm going to talk about time, light, simultaneity, space and time intervals and masses. Right. So let's see what I want to say about these things. So to describe the dynamics, and when I say dynamics, I mean the motion of a system, or more precisely, the evolution of a system in time. Yeah, that's what we will use the word dynamics for. To describe the dynamics of mechanical systems, observers such as you and me find it helpful to have a notion of time. Okay. I'm stating the obvious, but this is something very noteworthy. And this time is measured by a clock, which each observer keeps. And this time is used to index a sequence of events. Okay, so this is our experience that we see events like I woke up, and by an event of my waking up, I mean the time at which I woke up as well as where I woke up, right? So yeah, or the event of your starting your presence in this class. So you are located somewhere in your room and at 10:30 a.m. hopefully. So yeah, so that is what we mean by an event. Yeah, and time is used as a way to index events. Okay, now in Newtonian mechanics, one assumes that if there is a flash of light somewhere, okay, then all observers, whether it be you, me, or anybody else in this class, irrespective of their locations, receive the flash instantaneously. Okay, so a flash of light, I produce a flash of light here, of course, I will receive it. So will you, hopefully. I mean, if I break the walls and so on. But very importantly, we assume that all observers receive the flash instantaneously. There is no time elapsed between when the flash went off and when you received it. Okay, this is our very basic assumption in Newtonian mechanics. In effect, it means that light is assumed to travel infinitely fast. Okay, so this signal is a light signal, and we shall assume that it travels infinitely fast. Okay. Using such flashes of light, all observers can synchronize their clocks and assign the same time for a given event. Okay, so this event was my setting off a little spark. Yeah, on my clock, maybe I receive it at 11:04 a.m. Maybe on your clock, it appears to arrive at 11:06 a.m. Yeah, and Abhishek's clock, it arrives at 10:07 a.m. Now, each of us have set our clocks in some different way, but we can all recalibrate our clocks so that we all agree on the time at which this flash went off. Okay, so that is what we will do initially. We will reset all our clocks to agree on the time at which some event occurred, common event occurred, then we will say that all our clocks are synchronized. So from now on, we will assume that we are working with synchronized clocks. Okay. Yeah. Any question?
Is this assumption valid?
Well, it is. You can test it, and it is valid to very high accuracy. Yeah, of course, over very long distance scales, one does come to realize that perhaps light is not traveling infinitely fast. Yeah, so this is a long story. But from our common experience, it is valid to extremely high accuracy. So we are going to work under that assumption now. Later on, we will examine the question of whether this is departures from this assumption are relevant. And it is true. This is not exactly correct. Light does not travel infinitely fast. So we will have to account for that. So I will talk about that as well. But that will be later on. I'll make a few comments today, but the story will be continued later. Okay. Yes.
Sir, what is the use of a flash of light?
The use of a flash of light is to synchronize our clocks.
Okay, sir. Thank you.
Okay. Now, another consequence of this assumption that we have stated, I mean, it's not just an assumption, it's an assumption based on experience and based on experimentation. In Newton's time, it was believed to be exactly true. Yeah, and even today, it is not easy to find departures from this. We have to work hard. At least for many terrestrial events, this is an excellent approximation. Okay, another consequence of this is that two events, possibly at different locations, that occur at the same time for one observer. So I may be the observer, and the two events may be the one that Vishnu Ravi asked a question, and Onkon Mukherjee also asked a question. I may say that they both occurred simultaneously. Yeah, and if I say they occur simultaneously, then any other observer, such as Ryan Hota, will also agree that they occurred simultaneously, right? Because our clocks are all synchronized. Not just because our clocks are synchronized. If the simultaneity is the same concept for all of us, we say that it is absolute.
So can you explain this point again? Can you explain this point again?
Yes, let me repeat myself. Yeah. So suppose two events, I gave two examples, you asking a question and Vishnu Ravi asking a question or giving an answer. Yeah, suppose according to me, they happened at the same time. Then I will say they both happened at 11:03 a.m. today. I will assign that time to both those events. Yeah, but this is done after we have already synchronized our clocks and agreed about the time. Yeah. So then in your clock or on somebody else's clock or Ryan Hota's clock, he will also say that both these events happened at the same time. But I want to emphasize this had nothing to do with synchronizing the clocks. If two events happen together for me, it means that they happen at, I mean, the light from both those events is going to travel and reach me, but that light travels infinitely fast and reaches me instantaneously. It will reach you also instantaneously from both those events. So you will assign the same time to both those events. That is all. There is nothing deeper than this. Is that okay? Synchronization is a separate.
Where is light coming in? I mean, the happening of events and light.
No, see, how do you know that something has happened? You have to see it, or you have to hear it, or you have to do something. All right.
Okay.
Yeah. So that is how we convey signals. So we are now using light as our medium of transmission. And we are using the fact that light travels very, very, very fast and pretending that it travels infinitely fast. Okay. Any question about this statement? If I say some events are simultaneous, you will agree with me. There is not going to be any debate on that matter. That's all we are saying. And we give that statement a fancy term. We say that simultaneity is absolute and not relative. It is not observer dependent. All observers agree on the simultaneity of a pair of events.
Sir, does simultaneity ever make it difficult to distinguish two events?
Does simultaneity make it difficult to distinguish two events? No, because to distinguish events, you may have other means, like you trying to find the location. Yeah, I mean, the light arrived from the east side and the light arrived from the west side. So those two events can't be the same. Who will say that? So,
I had a question. So this might not be exactly relevant, but okay, so the fact that we use light as a primary means, is that accidental since we can see using light? So what if we saw using something else?
you could see using X-rays, and that X-ray may burn your eye, your pupils. But no. Apart from a joke, okay. So the fact that light travels very fast, we are exploiting that. And not only that, the fact that light travels infinitely fast for all observers to reasonable accuracy, we are exploiting that. The thing is that the setup of our framework will be more complicated if we used some other means, such as sound or transmission of electrons or transmission of atoms, right? It turns out that sound does not travel infinitely fast. We can detect the speed of sound, that the finite speed of sound, much more easily. And then the things will be a little bit more complicated. That's all. It is not as though the concepts of mechanics itself will have to be changed if we use some other means of synchronizing clocks. It's just that the process of synchronization or the process of assigning times to events will just be a bit more involved. We will need to account for the time lag between sound reaching me from Bangalore and sound reaching me from Kolkata. So I'll have to account for that before determining the times of those events. And that's a fine thing to do, just that our life will be more complicated. So, but to finish that story, you can use microwaves, you can use X-rays, you can use ultraviolet light. It's a remarkable fact of physics that all these things travel at the same speed, which is called the speed of light. So you have a lot of choice. You're not forced to use visible light and our eyes. You can use other detectors which are sensitive to these other gamma rays and so on. Is that okay, Anhad?
Yes, sir.
Okay. I have another question. One moment. Yeah, so Shyam Patankar has asked me, okay, the two events will occur simultaneously for both observers. Does that mean that their clocks will show the same time at the occurrence of the events? Doesn't distance matter? Yeah, so good question. This is re-emphasizing what we have said. So suppose I say that two events occur simultaneously. That means that even if those two events, one happened in Chennai, another happened in Kolkata, and I say they happened simultaneously, it's because the light from Chennai or Bangalore reached me instantaneously, just as the light from Kolkata. The distance doesn't matter because light travels infinitely fast. Okay, so distance simply does not matter.
Sir, is that mean? Does that mean that this concept of simultaneity arises because of the fact that the speed of light is infinite?
Yes, this concept of infinity, of simultaneity, is very much dependent on the assumption that the speed of light is infinite. So this concept of simultaneity is grounded on that. If you are going to discard that the idea that light travels infinitely fast, then this concept of simultaneity will need to be modified.
So the time of simultaneity may be different, or will there be also be same? The time of the simultaneity.
The time of a simultaneous event as reckoned by two different observers need not be the same if they have not previously synchronized their clocks. So your clock is running slow, my clock is running fast, then they will not assign the same time. Both of us will say they are simultaneous events, but we will assign different time.
Okay.
So
Fine,
to fix this problem, we must first synchronize our clocks, and then we will all have. Yeah.
Understood.
Okay, so that's great. And I have got also, Shyam has also says he understands. Very good. Okay, so now let me proceed with this. Okay. Now let me comment that these assumptions about light, time, and simultaneity were in line with common human experience and experimentation in Newton's time as well as today. Okay, so this is not some crazy assumption. It is in our common daily experience. It is very difficult to detect any effect of speed of light being less than infinity. Okay. Now, in Newtonian mechanics, one also makes some more assumptions. One assumes that the masses of particles, okay, I'll say a lot more about what a mass of a particle is, but I am having in mind that the mass of a particle is some number we assign to a particle that has something to do with its inertia. That is, a more massive particle will require a greater push to make it accelerate in the same way. Yeah, so but I will suppose that you have some intuitive concept of the mass of a particle, how much matter it possesses. So these are different ways of thinking about the mass of a particle. You can have any of them in mind. So we will assume that the mass of a particle, like a tennis ball, the scale of length and time are the same for all observers. So if I say this tennis ball, when I measure its weight or its mass as 1 kilogram, that's rather too much anyway, and somebody else does the same thing, they will agree with me. All right, no matter whether they are moving and so on. Okay, and if I say that this pencil is 10 centimeters long, you will also agree with me about its length. And that if I say that between two ticks of my clock, a time of 1 second is elapsed, you will also agree with that. Okay, so so one assumes that the masses of particles, scales of length and time are the same for all observers. In other words, distances, what has happened? Goodness. I have done something bad. Thank you. Okay, my pencil is back in action. In other words, distances like the length of a meter stick and time intervals like that between two ticks of a clock are the same for all observers. So now I'm saying these things just to keep them in the back of our mind. Yeah, these matters become more important when these assumptions fail, and it is at that stage when one starts thinking about these things more carefully. But nevertheless, it is good just to mention these at this stage. Okay. Now we have a further principle or experimental observation called causality. Our experience with physical systems indicates that they respect the principle of causality. In other words, cause precedes effect. Okay. For instance, a stone that is stationary is seen to move when it is pushed and not before that. Okay. So the movement of the stone is a consequence, happens subsequent to my pushing it and not before I pushed it. So that is what
What is the meaning of this? Cause precedes effect.
cause, the cause is karanam, right? Yeah, Tamil. So, or karan. Yeah. So it is the what.
Oh, okay,
Yeah.
okay.
So the effect is the outcome. Yeah. So the outcome is comes after the cause, right? That's all we are saying. So, but let me elaborate on that. I will say it in a different way. Yeah, but you say you understood. Very good. I mean, in other words, a swing is not observed to start swinging before I push it. This is our common experience. The principle of causality, said differently, postulates that it is not possible to send a signal from an event to its past. Okay, so we are reformulating this concept of causality by saying that it is not possible to send a signal from an event to its past. Okay, so I cannot communicate with events that happened before the time at which I wish to communicate. Now, given our Newtonian concept of time, all observers have a common notion of the past and future of an event. Okay, because once we have synchronized our time, our clocks, we all say that the current time is 11, 20, and 59 seconds, all right, today. So, and the past consists of all events that happened before that instant, and the future consists of all events that happened, which happen after that instant. So, let us say that again. The future of an event that occurs somewhere at time t0 consists of all events that occur at t more than t0. Okay, so this, once we have synchronized our clock, this is a statement that we can all agree upon. And the past consists of events that occurred at t less than t0. Okay, so this is, we have now introduced the concept of the past and the future of an event. And our statement is that we cannot communicate two events in the past.
Sir, can I ask two questions?
Please go ahead.
So first, sir, can we can we induce an event to occur at the same time? Not the past, but at the same time, at the present.
Yeah, we can induce that. Like I give a diktat that all students must be present at 10:30 a.m. for classical mechanics 1 lecture, and given that you are all very good students, you all log in at that time. So I have induced an event.
But sir, I am saying that suppose you tell me that, or tell all the students that at exactly 10:30 and they all join at 10:30 itself. Is that possible?
Yeah, it's fine. I mean, there is no exclusion that if one person has logged in, another cannot log in. Fortunately, Zoom permits you all to do so.
Yeah, so I am saying that you suppose I try to induce at event time t and the event occurs at time t itself, not in the future. Is that possible?
Oh, okay. This is some yeah, it's possible. Yeah, it's possible. Look, I mean, we have already done it in a sense. See, I have a flashlight, or I have two flashlights here. Yeah, I switch them both on simultaneously. Both produce flashes of light. That flashlight, the light travels infinitely fast and reaches two people, namely Ryan in Kolkata and Pinaki Mukherjee wherever he is. Actually, he's not even in this class. Yeah, so now the two events will be Rohan Hota receiving light and Mukherjee receiving light. Those two events are simultaneous. Both happened at the same time, according to me, and at that time that I decided. Okay, so we have demonstrated this possibility.
And sir, is it possible to state the effect of or causality in a general mathematical statement? Is it possible?
Yes, I think I have already stated it. I am saying that all events that occur, I mean, I've said it in two different ways. that it is not possible to send a signal from an event to its past. Okay, maybe I see the kind of question you're asking. We will do this kind of thing later on.
Thank you, sir.
Yeah, I think now is not the time to try to formalize this anymore. Let us work with this concept. I mean, you will have to set up a space consisting of all locations and also a time. So you have to set up a space of events, and then you will have to say which events lie in the future of which others, and which lie in the past. And yeah, okay. So, but no, your point is well taken. One has to make more precise. What does it mean to influence? Yeah, or what does it mean to send a signal? Yeah, these are physical concepts which I have used. You want to give some mathematical definition of which processes are called influences, or which processes are called signals. You can try to formalize such things. Yeah, there are frameworks where such things are done. But I wouldn't suggest that that is the thing to do now. Okay, now proceeding. And this is where our very brief caveat or disclaimer is coming up. These notions of time, simultaneity, and the universality of masses. When I say universality, I mean the idea that if I say I measure and find that this bottle weighs 40 grams, you agree with me that you also say it weighs 40 grams. So that is what I mean by universality of masses of objects, and the universality of space and time intervals. Unfortunately, or nature forced us to discard these concepts and replace them with more accurate concepts in the so-called special theory of relativity, okay, where the speeds of bodies or of observers could be comparable to that of light, and that speed of light is a large but finite constant in vacuum given by 3 times 10 to the power of 8 meters per second. Okay, so in with the passage of time, it was realized that light doesn't travel infinitely fast, and that has consequences, in particular for these notions of time, light, simultaneity, and so on. Okay, so yeah, so it had to be revised subsequently. We will talk about that later. But in retrospect, we can say that Newtonian or non-relativistic mechanics, as it is technically called, is a limiting case of special relativistic mechanics when the speed of light is infinite. So the subject of mechanics that we are going to discuss now, which is called Newtonian mechanics or non-relativistic classical mechanics, is a limiting case of special relativistic mechanics when the speed of light is assumed infinite. Of course, when we say that something is infinite in physics, we usually have to qualify that. What does that mean? We mean that the speed of light is very, very large compared to other speeds relevant to your problem. So if you are studying the motion of cricket balls in a stadium, that the speed of those cricket balls are much, much less than the speed of light, and non-relativistic Newtonian mechanics can be applied to their study. We just saw that 140 k's or so, that is the speed of a cricket ball, at least one bowled by a fast bowler. So the principle of causality continues to apply in special relativity, although the precise notions of past and future of an event needed to be revised. So so all that is the subject of special relativity, which we shall discuss later on. Okay, any questions about this? Okay. Okay. Yeah, I mean, you asked for being more mathematically precise. Well, I mean, suppose your space is simply two-dimensional plane, and events can happen at various locations here at various times, and you select one event which happens at this location at a certain time. Yeah, then you just need to say all events that happened before that. Yeah, and to do that, it is helpful to draw what is called a space-time diagram. Yeah, but no, sorry, I should not really be doing this. Let's do this later on when we discuss relativity. That would be a better place. It is possible to try to make these ideas a little bit more precise. Okay, so now let me come to other important concepts, and namely the degrees of freedom of a system, the concept of instantaneous configurations and trajectories. All right, so these are all technical terms which I wish to introduce. Okay, so let us begin with an example. A point particle moving in three-dimensional space. Yeah, so like a bee that is moving in my room, regarded as a point particle, has 3 degrees of freedom. Okay, and why do I say that? We need 3 coordinates, namely x, y, and z in Cartesian system, or r, theta, and phi in the spherical polar system, to specify the location of the particle at the initial instant of time. Okay, so we choose some instant of time, call it the initial time, and I need to say how high above the ground my bee is, how far from the window it is, and how far from the wall it is. Okay, so I need to specify these 3 numbers to locate the bee at that instant of time, and therefore we say that a particle moving in 3-dimensional space has 3 degrees of freedom. So said differently, we could locate the particle anywhere in 3-dimensional space initially. So its 3 initial coordinates x, y, and z can be chosen arbitrarily at the initial instant of time. And we say that x, y, and z are its 3 degrees of freedom, and that the number of degrees of freedom that this particle possesses is 3 in number. So this will be a very useful concept, and it turns out a source of confusion as well. So I have tried to, I will try to emphasize it and elaborate on it. So let's look at another example. Suppose you have a system of particles, not just one, but several of them. Then the number of degrees of freedom is the number of real parameters, that is real coordinates, needed to specify the locations of all the particles in the system at the initial instant of time. So you pick an instant of time, and you need several real numbers to specify the locations of all the particles. Okay, so the number of those in coordinates needed is called the number of degrees of freedom. So please tell me, suppose you have 2 particles moving in this room or in your room, how many degrees of freedom does that system possess?
6.
That's indeed right. You would need to tell me the coordinates of the first particle, x, y, and z coordinates of the first particle, to locate the first particle. Yeah, and for the second particle, you would need to tell me its Cartesian coordinates, which are another 3 real numbers. Okay, so we would say that a system of 2 particles moving in 3-dimensional space has 6 degrees of freedom. I would like to emphasize that the number of degrees of freedom does not depend on the nature of forces between particles or external forces acting on the particles. Remember, I just said 2 particles in this room. I didn't say that the 2 particles attract each other or repel each other, or under the influence of gravity, or under the influence of my hitting them, and so on. All right. So irrespective of the nature of forces, the number of degrees of freedom is defined. So for a free particle, that is one that is not subject to any forces or external influences, that's what we mean by a free particle. So a free particle That's a very valuable concept. A free particle is one that is not subject to any external influences. Yeah, a free particle or a particle that is subject to Earth's gravity, moving in three-dimensional space, both have 3 degrees of freedom. So it's something well worth understanding. No matter what the type of forces in operation, the number of degrees of freedom is the same. Okay, let me go to another example, which will clarify things further, I hope. On the other hand, a point particle that is constrained to move along a fixed wire has only 1 degree of freedom. Okay, so suppose my wire is this thing, this is my wire, and I contemplate or think about a particle that is moving along this wire. Okay, it cannot go off the wire. It's a point particle, moves only along the wire. I mean, the wire is infinitesimally thin, let us suppose, and it moves along the wire. We would say that such a particle has only 1 degree of freedom. Now, what is that degree of freedom? How do we quantify it? Let us see. Well, we need one coordinate which could be chosen as the distance along the wire from one endpoint to the instantaneous location of the particle. So this is my wire again. The particle is located here. I will assign a coordinate to the particle, namely the arc length from the starting of the wire to that point. Okay, so that is my coordinate. It's the arc length to the location. Yeah. So that one number, which is a real number, can be used to specify the location of the particle at a given instant of time. So we will say that such a particle has only 1 degree of freedom. So this is a picture. Particle moving along a line or along some curve has only 1 degree of freedom. Doesn't matter that that curve was embedded in three-dimensional space. That is not relevant. Okay, any question so far? All right, let's go to another example. A particle that is constrained to move on a spherical surface, such as the bob at the end of a rigid rod whose other end is attached to a fixed pivot. Okay, so I have in mind some situation like this. I have a bob. My bob is just not very big. Anyway, the bob is this end of the pen, and my rod is the pen itself, and the pivot is holding the other end of the pen fixed. And this end of the pen, which I can say is the clip of the pen or something, has to move only on a sphere, right? Because the center of the other end of the pen is held fixed, so it cannot go farther and nearer. It has to move on a sphere. Such a particle, such a bob, has 2 degrees of freedom because it can move on the surface of a sphere. So a particle moving on the plane again has 2 degrees of freedom, and the 2 degrees of freedom could be the horizontal and vertical coordinates, for instance, or a particle moving on a sphere. We could use a pair of angles like the polar angle and azimuthal angle to specify the location of the particle. Okay. Any questions?
Sir, one thing.
Yeah.
How do I distinguish two particles if they're in the same location, but one is constrained in a certain sphere and one is not constrained? How do I distinguish those two?
No, wait. You said one is on a sphere, another is somewhere else, is it?
No. I mean, two look. I have taken two different 3D spaces.
Okay.
Both particles have the same coordinate in the two 3D spaces in R cube. But one is constrained to move in the unit sphere and the other is not constrained as such. Okay. How do I distinguish them?
I mean, we are okay. You are asking some question. I am not talking about distinguishing particles over here. But your question is, of course, a fun thing to think about. No.
My question is like, how do I say that this is constant and this is not constant? What is the definition of a constraining? Like what's like, because the initial coordinates do not let you see whether they move in what direction or not.
Good question. No, somebody has to specify and tell you, or you have to do experiments and figure it out. So this is not, it is not some self-evident thing. Yeah, so you have to make observations at lots of times and deduce that, okay, this particle is not able to go off the sphere, and therefore I should treat it as a system with 2 degrees of freedom. It is, yeah, your point is well taken. Just by seeing, okay, I need to, perhaps I did not state my definition carefully enough, but it is not that you have observed the particle at one instant of time and know how many degrees of freedom it has. No, this is a property of the system as a whole. We are saying what is the possible places where the particle can be at the initial, all possible places it can be, not just 1 or 2 which you observe, all possible places where the particle can be. How many coordinates do you need to specify all of them? And that is the number of degrees of freedom.
So I have a region of possible places and I am trying to find out the dimension of that region.
Dimension of that space, indeed, very much so. Yeah.
Okay, so the map needs to be continuous, right?
Which map are you referring to?
Okay, I didn't like. Okay, so when you say like the cardinality of all of these sets is the same. So when you say 1 degree of freedom, 2 degree of freedom.
No, the cardinality of the set of possible instantaneous locations is infinite in both these cases, right? Because they're infinitely.
It's this like it's you can have like a bijection between them.
True. But no, we are not. This is not a question about the cardinality of the set of possible locations. Those two are in bijection. You are quite right. We are talking about the dimension of these two spaces. Regarded.
So how would you define a dimension?
We have given a very practical definition. How many coordinates you need to specify the locations?
But well, since the cardinality is the same, we need to
no, cardinality is nothing to do with this.
But we could use 2 coordinates, right? As long as like we could like map everything to the plane and use to use 2 coordinates.
Oh, no, we are not mapping anything anywhere. We are taking the space as given in the system.
But well, so the problem is we need to identify each point on the space with the tuple of a real number, right?
Sir, I think what he is saying is that I take a sphere, I can map all of the points, I can make a bijection with a line, and I can use 1 coordinate to describe all the points on a sphere.
Okay, you are quite right, but yeah, but the map that you would use to convert a sphere into a line is some very bad map that does not preserve any of the physical concepts that we wish to use to describe this particle. Yeah, so if that is what you meant, that the map has to be reasonable, I totally agree with you.
What could you elaborate on reasonable?
Yeah, so the space in which the particle is moving, you can consider it as a topological space or a manifold, and the maps we are considering are charts, and they are all having to be continuous maps from that topological space to your Euclidean space. So we are considering only continuous maps which do not change dimensions, certainly. I don't know if that language is of any use to you. Anhad was asking, right?
Yes.
Yeah, please. No, are you okay with what I said?
Okay, sort of like.
Sorry.
But like, because for example, like you could like there's a continuous mapping from a line to a 2-dimensional space as well, right? So
okay.
Is it?
I don't know. See, I am not very sure. I don't know what topology you put on your plane and on your
Like
line.
a surjective map from a line, like there's a space filling curve, right?
A space filling curve. Okay.
So does it, so like, so that means that a 2D space is like 1D as well? No.
No. That map is very discontinuous. The notion of nearness is severely warped by this map, because your space filling curve, that curve may come close to itself after a long time. Then those 2 points are far away on your curve, but they are nearby on your three-dimensional space. So this concept, this mapping you have used to put your curve in the plane is some horribly discontinuous map. We have to preserve the notions of neighborhoods, nearness, and such things. Otherwise, all hell breaks loose.
Sir, can you please explain why, if the particle is moving at a sphere, only 2 degrees of freedom?
Yeah, because to see, I have to ask the question. We are told the particle can move on a sphere. That is what the person is telling you. All right, that's what the experimenter or the person setting up the apparatus is telling you. I am going to study a ball that's moving on a sphere. So you as the who is studying the system will say, okay, what are the possible initial locations at which the experimenter could place the particle? Could be anywhere on the sphere. Now, to specify those possible initial locations, I need to specify the latitude of the particle and the longitude. If I specify these two, then I know where the particle is. Okay, maybe there are some exceptions, yeah, North Pole and all, yeah. But by and large, I need 2 coordinates to specify them. And in that manner, I determine that the system has 2 degrees of freedom. Is that okay, Ankon?
Okay, but if it was an ellipsoid, then it would be 3.
Okay, I need to understand what you mean by an ellipsoid. What I understand by an ellipsoid is the surface of a egg. All right. Now, if a particle is moving on the surface of an egg, how many degrees of freedom does it have?
2.
2. Thank you very much. So that was that Krishanu.
Yes, sir.
Yeah. So, okay, Ankon, do you agree? So it doesn't matter whether it is the surface of a sphere or the surface of an egg or the surface of an ellipsoid or surface of the earth.
But the
All of
radius
them
is
have.
then changing. I mean,
No,
are you
radius
saying-
is changing, but you still need to only tell 2
It
coordinates.
is like walking on Earth, I think.
Yes, walking
On the
on
road
Earth.
surface,
See,
but
I mean,
not increasing the height.
indeed, you are
But
not increasing the height. So see, the Earth also is not a sphere, as you are aware. It is some prolet ellipsoid or something. So it is bulging at the equator, flattened at the poles. But we still need only 2 coordinates to tell me where I am. Yeah. No, if the particle can fly off the surface, then I need a 3rd coordinate. Yeah. I hope that helps you to think about it. Are you okay with this, Ankon? Okay, I have lost you. Fine. Any more questions about this idea? Okay, I forgot who was asking about that space filling curve and so on. Okay, I hope I have.
Space filling curve was me.
Anha Chaturvedi, yeah. Okay, so I hope I have tried to address your question. Is there any further thing you have on that?
Nothing further.
Okay, fine. Yeah. So as it turns out, we have run out of time, but yeah, we have introduced some very important physical concepts in modeling mechanical systems during this lecture, and I hope you will go over them once again. Please go ahead for your other classes. If there are no other questions, we shall halt and so tomorrow morning at 10 a.m. we have a tutorial session where the solutions to problems set 3 will be discussed. I will communicate that to you. Any other questions?
Sir,
Yeah.
suppose I say that A ball crashes into B ball and B ball has been crashed into by A ball, are these two different events or the same event?
I mean, this is an impact of two bodies that happens somewhere at some time. So it is an event. You can describe that event in different ways.
Okay, sir. Thank you.
Yeah. Okay. That's like giving the address of a location in different ways, different coordinate systems or different languages and such things. All right. Any other questions? Fine. If not, thank you for your attention, and we shall. I will communicate to you about the tutorial tomorrow and the class on Thursday. Okay. Thank you.
Sir, do we also assume, sorry, sir, one more
Yes.
question.
Okay. Go ahead.
But do we also assume that one thing like if a ball hits another ball, we assume that the shock wave through that ball is instantaneously transferred, right?
Okay.
I mean, if I suppose 3 balls in succession, I hit the first ball, the third ball instantaneously comes out, right?
All right. I mean, I don't know. You are telling me a certain setup. Please go ahead.
In a rigid body.
Okay,
So,
fine.
but as far as I know, this material transfer, this occurs at the speed of sound, like material wave. Yeah.
All
so
right.
do we also assume therefore that the speed of sound is infinite?
No. I mean, you are modeling a system, so you need to model it to the accuracy you wish to be satisfied with. So, I mean, if you want to account for the finiteness of the speed of sound, of propagation of disturbances in this medium, you have to do it. And it is not true that a knock on one side of the ball will reach the other side of the ball instantaneously. No, but no, if you are modeling it as a rigid body, then you're already violating the principle of finiteness of speed of sound. A rigid body, by saying it is rigid, cannot vibrate, then it cannot propagate sound through it. Or rather, the sound will go infinitely fast through it.
Thank you very much.
So one needs to be careful when one says it's a rigid body, then you are sort of excluding certain phenomena.
Okay, sir. Thank you very much.
Okay. Anything else now? Okay. If not, have a good afternoon. All the best. Yeah.